Thank you for being here. My name is Ebukai Bekwe,
I am Juan Barrientos.
and this is our project, Go Baby Go 2023. Go Baby Go is a nationwide program that was founded by Dr. Cole Galloway in 2012, and it was developed to assist young children with physical disabilities and is to offer a break from a movement aid such as a wheelchair and to give them an opportunity to socialize and have a fun time. What are our objectives? In this project, we focused on a few key things. One of them was to translate a pulse width modulated signal into a DC wave, or to reduce a DC wave from 12 volts down to 5 volts because of the computer that we're using, the Arduino, can only handle that amount. We also wanted to design a compact circuit that could fit into the location of the car where it's meant to be. Also, we took into consideration safety. That was a very important thing for us. We also used software to translate inputs in order to get desired outputs. In this project, you will notice that my partner Juan and I used two different methods in order to achieve the results so as to give an alternative to our customer.
So, as he mentioned, we have to deal with pulse width modulated signals. This pulse width modulated signal is very popular when dealing with a signal that's neither high and low, but in between. This can be things like robotic arms movement, temperatures, and in our case, it'll be an electric motor. As you can see, here's what the pulse width modulated signal looks like, and the analog right that you see on the right translates to what the Arduino will be outputting in terms of the pulse width modulated signal. Here's the signals taken from the car. As you can see, we are dealing with a pulse width modulated signal. The first one is at its first speed, the second one is at its second speed, and the third one is straight DC whenever it's on full speed. So here's the Arduino Nano. Me and Buka are familiar with this through our microcontroller microprocessor class that we took. We actually used Uno, but this is the Nano. It's smaller, it's a little less expensive, but so we decided to use this, and we also had this from the previous teams. As you can see in the pins section, it has 6 pins for a pulse width modulated signal, which what we will be working with. And on the power, it specifies a maximum of 5 volts. So that's why we need to reduce the voltage coming from the motor controller into the Arduino so we won't damage the Arduino itself.
Over here, you can see the motor controller that we use. We use the Citron motor, and this is our 5 volt relay. We'll talk more about these in subsequent slides. So we designed a simple block diagram to show the entire process of the Go Baby Go car. The blocks in white are things that were pre-existing, designed by the manufacturer, while the blocks in blue are things that my partner and I added into the process. So when the pedal of the car is pressed, an input is generated, which sends a signal to the original motor controller. From the motor controller, the signal is then reduced either using the RC circuit, which is one of the alternative methods, or the voltage regulator circuit. The voltage regulator circuit or the RC circuit would then send a signal to the Arduino Nano. Now, the Arduino Nano would power the 5 volt relay. The 5 volt relay is usually open in its default setting, but when it gets that signal, it will close, and then the Arduino Nano will also send a signal to the motor controller. When that 5 volt relay closes, it will get power from the battery, send a signal to the car motor, which causes the motors in the car to move the wheels.
So here's our first method. This is a prototype that we did for the testing. Later on, you'll see a more condensed version so that it can be easily mounted into the vehicle. I'm using specifically the LM78L05 voltage regulator. As you can see, here's where I implemented it. They were soldered on and covered with heat shrink for safety. and I also use ferrules to put into the Arduino to make it more safe and fit. So here's the specifications for the voltage regulator. There are some conditions that needs to be met with this. It needs to be between 7 volts and 20 volts, and we're right around the middle at 13 volts peak. You can also see that the maximum current that it'll output is 140 milliamps, which is safe for the Arduino. So if anything, this will go out first before it goes to the Arduino. Using Multisim, this is software that we use in our classes like Electronics 1 and 2. We were able to simulate what the output was from the voltage regulator before we started implementing it, so we wanted to make sure. As you can see, here's more of the wiring. The voltage regulator shown on here is not the exact one we use, since the one we used wasn't in the library, but it's very similar and it does the same function. As you can see in channel B, I fed it a square wave at 13 volts, which mimics a pulse width modulated signal. And channel A is the output after it comes out of the voltage regulator, and we were able to get 5 volts, which is ideal for the Arduino Nano. So here's a schematic diagram with the voltage regulator. This is more of a in detail schematic, unlike the block diagram. Most of the components that were in the block diagram you can see here. For safety, everything was wired after a fuse for coming from the battery. So if something happens to the battery, the fuse will go out, causing everything else to shut down. As he mentioned before, we do have a 5-volt relay. This ensures that the motors aren't getting any power from the battery unless the Arduino Nano is on. And the Arduino Nano is powered by a 12-volt signal that we found in the car that only turns on when the power button's on. So we had a little issue finding that what powered the Arduino, but luckily we were able to find a wire that is only live when the power of the car is on. So this also keeps the car from consuming any power needlessly while it's off. So the Arduino Nano can only turn on when the power is on. So here's a function that we created to read the pulse width modulated signals, because in my method, we're still dealing with the amp pulse width modulated signal. This function times how many times the signal is high per cycle, and this can be changed to the user's needs. But we needed, so we thought of it and we decided what's important, and as soon as the signal goes high, with the ball and if statements, we can determine the output that we want. So this was needed to know when the pedal or the remote control was initiated. And the Arduino Nano outputs from 0 to 255, which you'll see later how that translates to the speed of the car.
So the alternative method that we designed was a simple RC circuit. If you're not familiar, an RC circuit consists of some resistance as well as capacitance. So here you can see the resistors that were used as well as the capacitor. This was an early prototype, so over subsequent builds, I cleaned up the circuit. I made it more compact so as to fit in the position where we wanted it to be and prevent any kind of accidents. So from our Circuits 2 class, we learned about Fourier analysis, and we used this really to double check our simulations to ensure that we would have as little ripple as possible. Ripple is basically noise. We wanted to make sure that there was little disturbance to the output that we were getting. I ran a simulation using Multisim to show how a PWM, which we talked about earlier, would change into a DC wave. So over here in red, you can see the box looking is the thing that's the PWM, and the green wave is the one that's the DC. This is a schematic diagram that was designed using AutoCAD to show you, like Juan talked about earlier, the whole part of the process where you can see the Arduino Nano that we used, and you can see the RC circuits both of them.
So here's the design we came up with to mount it to the car. This was designed using Fusion 360. You'll see later on how we implemented this, but we basically, everything that you see here, we pretty much had in the shop. This consisted of using standoffs, sheet metal, and what you see in the middle is actually the motor controller. So when you buy it, it already comes with hose where you can put standoffs and stuff. So, and then you see your 5-volt relay and the Arduino Nano. Now the Arduino Nano is using a mounting mechanism that Arduino sells. I couldn't put it in here, but you'll see later how the Arduino Nano actually sits. We came up with this, you'll see in later slides how it conveniently goes in the back.
So this is one of the cars where on the right you see the RC circuit. It goes into that point there. Those were where we drilled the holes in, and it can be conveniently removed in case any changes need to be made to the circuit. And this, like Juan was saying, this was what we designed in order to install the circuit into the back of the seat.
And here's on the other card. So we did two vehicles, the blue and the white one. Each one had each method into it. As you can see, like he said, this the back conveniently comes off all in one piece. So we ever wanted to make some adjustment, we'll just disconnect it from the terminals and just pull everything out without having to, just gut everything out. This is also behind the seat, which is bolted on. So you can't really access it to it unless you want to access to it. So any child or parent won't be able to touch or do anything with this. As you can see, the Arduino Nano is facing forward. So if we ever wanted to change the speed or the output, it's just take the cover off and plug it in. It's easy to access, and change can be made on the fly. So here's a video of the white and blue Audi. Both of these are configured to go at different speeds, just to show that it actually works and you can adjust the speed. Both of these cars were already decelerated. That's why they're both going at the same speed. But at some point, since as you can see here, the white one is configured to go a little faster, it will take it off faster. And this can be changed depending on the child's needs. If the child is a little more scared, or you can slow it down like the blue car, or if the child, as it progresses, he can go fast and you can speed it up so he can enjoy himself. And both of these were, there's a 28-pound weight to mimic a child's weight. So they're both strapped on, and yeah, as you can see, it was working.
So like we said earlier, two of our goals was to make the car safe by reducing the initial acceleration and top speed. And this video shows that we're able to achieve both of those things. You can see that the left car has a higher top speed than the car on the right in blue. Here you can see our Gantt chart, which we're at the end of this now because we have two of our deliverables, which are two cars. On the right there, if you leave through that door, you will see one of the cars there for display, and we were able to come to the end of our Gantt chart. Acknowledgements, we'd like to thank Dr. John Ventura, we'd like to thank Dr. Eric Welch, Thomas Podesta, Mr. Henry Rhodes, Dr. Vali Ahmad, and late Dr. Azire. Any questions? Joseph?
Yes. So, pardon my ignorance, but I don't know if I caught on properly. So, what was the point of adding the RC circuit into the design? Like, when did it become an important part of the project?
So, two of our goals was to find out how we can either translate a PWM to a DC, or how we can reduce the amount of voltage going into the Arduino Nano. Why do we want to reduce the amount? Because the manufacturer of the Arduino Nano has made it to where it can only handle up to 5 volts. So we use that RC circuit to reduce the amount of voltage going into the Arduino Nano.
So this car is focused more on children with disabilities, and you guys looked into a way that sort of has deep pedals.
Yes, we're actually supposed to be collaborating with the UTCHS, but we really didn't get feedback from them this year. Normally, we would either change the seat, push, instead of the pedal, you'll have a button on the steering wheel. And these are all like superficial, adjustments, so, you know, it's not as complicated. We were mainly focused on the electronics of it to reduce it. We had in the past where you just add, little PVC rails for, or different seats, and like you said, a different, method of, pushing it. This also, we controlled it with RC, so normally, whoever's taking care of the child would be able to dictate the speed, and the child is not able to, drive it themselves. Yes?
Did I hear correctly that in order to change the speed, you have to go to the board and change the setting on the board? Is that-
Yes, so if there, for any reason you need to change the speed, we have a code. I didn't display the code because it's long and complicated, but, it's a global variable in which you just hook up with via USB and just change that one, variable, and it'll change the speed on the car. You know, normally, we would have to go out there and do it, or, you know, somebody with the code can just plug it in and change it, and it'll be a different speed.
Okay, then my question on that is that if that's what is desired, why did you guys set it up in such a way that by just pushing a button, 1, 2, 3, you can change the speed rather than going to the code, changing the code or connecting to the board to do that?
Well, that will make things, a lot more complicated, because it is a code. Usually, parents will dictate what their child wants, so we want to make sure that the parents were okay with it, so we'll only be the ones to change it. You know, it makes issues to where someone doesn't accidentally change it for some reason and have the kid, go faster than you should.
To add to Juan's answer, the cars have 3 options of speeds. We call them gears. 3 options of speeds that the guardian or parent can select. However, to increase or decrease the top speed that the car can reach, we would need to go in and do more technical changes.
Okay, that's what I was asking for. So
Yeah.
there are options that they can choose different speeds. Okay, thank you.
Any other questions? Thank you for your time. We appreciate it.